Hello and welcome to our second video on resonance. Just a brief review of electron arrow pushing, that's electron movement. So for example, there might be an oxygen here with a lone pair. You want to draw your arrows showing the movement of two electrons, showing where they're starting, where they're ending. This would be perhaps a bond forming reaction. While over here we have bond breaking. But also maybe forming as well, depending on where they're going. This would be a situation more familiar where it's the pi bond of a double bond, forming a new bond while it's breaking as well. So the goal of electron arrow pushing is to understand and predict reaction mechanisms and outcomes, in other words, products. We're going to revisit this topic later in depth, and we're going to use it all quarter. So read that section in Klein especially. This system applies to resonance arguments. Okay, so on to resonance. Resonance is an analysis, not a reaction. So the analysis is used to reveal the stability of molecules, but also to predict reactivity, so it is related to reactions. In the early going, to visualize better, you might want to draw in all your implied atoms and lone pairs. So I did that over here on the right so you could see what this molecule actually looks like. This is the classic case of the resonance in benzene. So electron movement in benzene could be represented like this in resonance drawings. We have a double arrow to show resonance. That's what that double arrow is always used for. And the result of the movement of these electrons is this structure. And you can go back in the other direction by drawing electron arrows like this. So this resonance analysis of benzene reveals two equal contributors. You could even say equal energy contributors. There's some other terms that you might want to be familiar with. This concept of the electrons moving around can be described as delocalization and as conjugation. So you might want to file those words away for future reference. Delocalized electrons indicate that they're moving all around over a wider range of atoms. Sometimes benzene is drawn like this to represent that. Now on to more resonance structures. One of the principles is that the atoms don't move, just the electrons. To get from this resonance contributor to the one on the right, you can move electrons like this. That brings these electrons up onto carbon. This is a poor resonance contributor. Why? Because you have electron density on the less electronegative atom carbon instead of on the more electronegative atom oxygen. So keep that in mind. Here we have a simple case of these electrons moving over to here in the direction of a plus charge, which you would expect is the direction they want to go, and you can get back in this direction. I would say these are equal contributors to the stability of the molecule and to the reactivity. See how they're the same in almost every respect. Another principle of resonance drawing is that the more resonance contributors you can draw, even if they're not the most favorable, does lead to more stabilization. This first case shows an error, basically, where you would think, okay, I'm going to bring these electrons up here and up here toward the electronegative oxygen to give me this structure. Unfortunately, we have an issue here, and that is the octet rule is broken. So, no good. Now, we can draw resonance contributors in a different way for this, involving bringing these electrons down and then up onto the carbon atom like that as a first pass. And that gets us to this resonance contributor. Where charges are created, however, it's a legitimate resonance structure. You can continue this in successive stages. Bring these electrons up onto carbon. So you can bring electrons up onto the atoms as well. Gets us to this resonance contributor. Plus charge there. Minus charge there. And one more time, bring these electrons down, up onto that carbon. Draw this resonance contributor. So we got a lot of resonance contributors here, none of which are particularly stabilizing, but as a whole, because we can draw so many of them, it has a stabilizing effect, and that makes sense because you're just distributing electrons over more atoms. More resonance contributors, more stabilization. Okay. The creation of charges is generally not favorable compared to not having charges created. So here we have electron movement like this, which is the classic electron movement in this situation. These look like equal contributors. However, you could legitimately draw a resonance form like this, move these electrons up, creating these charges here and here. Now you got 3 charges. That is not a good contributor. So this resonance analysis would say that this form here is a better resonance contributor than surely this form. Finally, you want to keep electronegativity in mind. We kind of already mentioned it. In this case, you can bring electron density up toward the more electronegative atom oxygen to give you this guy. And I left out a charge there, notice. So you got to be careful with your formal charges. This is a resonance contributor, but this is probably your better form. More representative of how the atoms, how the molecule exists. You probably don't want to bring electrons down away from this oxygen, although it is legitimate, it's just not very useful. You create a negative charge on carbon and a positive charge on the more electronegative oxygen, so this one's poor. And this analysis helps us understand the reactivity of carbonyl groups, which is typically the addition of something with a negative charge. We often call them nucleophiles, coming in and forming a bond there. That's a little glimpse of the future. And just a final note, what you see here is not resonance, even though the electron arrow movement looks similar. It's a reaction because you're creating a new connection between the 2 carbon atoms on the end. You're creating a new compound, so that's a reaction and not resonance. It's not just electrons flowing around the same compound.